Alrighty. And we are finally good. Alright. Sorry about the delay. I was running into a bunch of trouble with some Git stuff on this machine where I wasn't able to get the latest version of my branch, which is super fun. So I ended up just having to copy the completely reset version of the branch from a different computer, which was super fun. But we're here. We're back in WebAssembly. And today we're going to be going back into raw WebAssembly text, and we will be looking at this time a bit more advanced control flow. So last time, if you guys remember, we looked at this accumulate function and then the average function here. And we looked at a loop here, a block and a loop, and then there wasn't any if, but we did a conditional branch here. And we're going to be looking at some more stuff that's a bit more advanced than this, and we'll be looking at it in the context of Base64 encoding. So if you're not sure what Base64 encoding is, I'll just go through it real quick. It doesn't matter too much. It's just more about writing the code. But I have, so in the previous PowerShell video that we did, we wrote, we essentially just had a function that calls a C# function to encode a string of bytes. So Base64 encode, say the string ABCD, and it outputs this little string here. And what is special about Base64 is that you can take any string of bytes. They may not even be printable, so they can be like the bytes 0, 1, which doesn't have a printable character associated with it, but it will convert into some form of data that you can print. So this is helpful when looking at the web and you want to transmit something over with a URL or in a cookie, something along those lines. This really does come in handy. So we will start with our C implementation. We'll write how do we encode something in Base64 using C. We will then compile that using emscripten. And then we'll see what the WASM, the compiled code is. And then from there we will write our own implementation and compare the two. So the reason why we're going to be doing the C implementation first is just so we have a reference. So base64.c, base64c.c, just so we can differentiate. Okay, I don't want those things. Okay, so let's start with a couple things here. So we're going to essentially just output. So we're going to define one single function, character pointer, Base64, or sorry, we'll say B64 encode, and we'll pass in an unsigned character pointer data with an unsigned integer length, and then we will also want to output a number of bytes that we wrote. So actually, for consistency, what we'll do is we will return an integer. So return an int. I'll just make these all normal just so there's less text. We'll return an integer, which is the number of characters we wrote, and then we will pass in a pointer to the output. And this pointer has to have already been allocated to some amount. So what we'll start with is determining what the output length will actually be. So the way Base64 works is we have our bytes. So for example, this ABCD, that's 4 bytes. Each character takes up 1 byte, but you could also have hex characters. So something like, if I go into Python, something like this. Can I do CLS? Is that? No, it doesn't work in Python. But if I want to do something like 0x01, this is 1 byte because it takes up 2 hex characters, which each has 4 bits, and that has the value 1. So we can encode this bit, this 0x01, as a byte into Base64. So it's going to take a group of 6 bits, and it will represent that using one of 64 printable characters. So we're going to store those 64 printable characters in a table up top. So we're going to have a character B64 table, and it's going to have, actually we can just have this as a character Base64 Base64 table, and it will have 64 characters in it, or I guess 65 if you count the terminator, but we can just represent this as a string. So it starts with all the capital letters, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, all the way up to Z, then the lowercase P, Q, R, S, T, V, W, X, Y, and Z. Then we have our numbers, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we still have two more characters, a plus and a minus, or plus and a divided by sign. So this is a total of 64 characters, not counting the terminator. But essentially we take our data, which is in bytes, so groups of 8 bits. So I'll give you an example. How do I want to do this? So let's say we have the string hello, and this will then map to, let me actually get, sorry. This will map to the bytes 72, 101, 108, 108, 111. Then this in binary becomes, so let me give me 2 seconds. 1, bin 108, bin 111. So this maps to a couple of things. So the 72, if we're considering 8 bits, it's 0, 1, 0, 1000. Then we have 01100 101, 0110 1100, and then finally this actually repeats twice. And then finally for the 111 we have 0110 1111, like so. And so these are all in binary. And the way we want to map these is we take groups of 6 bits, so these first 6 bits right here, and these 6 bits also represent a number. So in groups of 6 bits we have 010010, then we have 0000, because we're taking these 2, right, space there, then 4 from here, so 000110. That's another one. The next group will be these, so we took those 4, then we have 0101, these 4 and 2 from here. So 0101, 01, like so, and then these 6. And then we can go so on and so forth. But the point is that this maximum value of 6 bits, we can have a maximum value of 63. And if you'll notice, this table that we just wrote has 64 characters in it. So we can go from 0 to 63, which map to indices here. And these are all printable characters. So I'm going to now convert these back into decimal. So let's see how this works. 0B01010, 0B0001110, 0B10110. Alright, so these map to 18, 6, 21, 44, ... And then we now use these numbers as indices into this little table here. And whatever character we find at index 18 maps to this first character. And so we take 6 bits, we take groups of 6 bits and we pad with zeros until we're done. And so if you wanted to see the Base64 encoding, B64 encode hello, we'd get SGV SBG8 equal sign. So if you can see, S I believe is the 18th letter in the alphabet, or actually the 19th letter in the alphabet. So it has index 18 in this string here. So this S right here, that's the first one. And then G this is index 7, or index 6, sorry. V is index 21. Lowercase s is index 44, and so on and so forth. So we're going to be essentially just parsing these bits and then taking their maps in a table. And we'll start just by, going through it. let's first calculate the length that we're going to be returning. So an integer length is equal to, and if you'll notice, we have 4 characters, or 4 output characters for every 3 input characters. That's just the ratio. We have 8 bits output for every 6 bits input. And a way to represent that using only integers is to say 4 times input length. So this should be out length. So we have 4 times the input length plus 2 divided by 3. So you can see the ratio of 4/3 here. And then this plus 2 just ensures that with an integer division, we will get the proper values. And another quick note, you'll notice that we have equal signs sometimes here, and you didn't see that in the table. That's just the padding bits. So if you have a 0, first of all, if it's 6 zeros, that maps to the letter A. But if we have exceeded the input string, we pad it with equal signs so that the output base64 string is a multiple of 4. So we want to have either 4, 8, 12, 16, so on characters in our encoded string. So that's why we do this here. All right. And then we're going to start with our stuff. So we have our output pointer, and we're just going to go through the input string. So we have 4 integer I is equal to 0. J is also equal to 0. So these are 2 initialized variables. I is less than input length. And we have no increment step because we will be taking care of the increment within the loop. So we want to iterate through each triplet. So this loop here will iterate through 3 octets and output 4 base64 characters. So we're just going through, because if you saw in the example, every 3 characters, so we have in every 3 bytes we have 24 bits, and that's a multiple of 6. So every 3 bytes, 24 bits maps to 4 6-bit groups. So we're just using this as multiples, as even multiples, so that we can have a bit of a it's a bit easier to manage. All right. It's a bit easier to code, I should say. So we'll start by saying that we have an unsigned integer octet A, or octet 1 rather, is equal to, if I is less than the input length, or if I is less than the length, then we take the data. So we have data is stored here. I really wish I could collapse this. Do I need to? I really wish I could collapse this top bar. It takes up so much space. How do I toggle panel? No, I don't know. I don't want that. Customize layout. I don't even know what I'm doing. All right, we'll leave it at this. I don't need that. Does that do it? Nah, not really. Okay, all good. So I'll just zoom out so you guys can see more. So octet 1, if I is less than length, then we take the data. So we have data at I++, and we advance the cursor. Otherwise, we take a 0. And we'll take another octet. 2 is equal to I is less than length. Data at I++, and you'll see that this is the same. So we essentially just take 3 bytes at a time. And if we exceed the data, then we just take a 0. And we need to be converting these data to an unsigned character. Actually, we can just make this an unsigned character pointer data there. All right, and then finally we have unsigned int octet 3 is equal to I is less than length, data I++:0. And then this cursor, will be compared in the next iteration of the loop. So then we're going to take these 3 bytes and we want to combine them so that the first bit that we read stays on the left. So we essentially want an ordering that is octet 1, octet 2, and octet 3. And we want this to be 24 bits. So concatenate to get 24 bits, like so. Because these are each 8 bits, so we want to concatenate them. Oh, concatenate. And an easy way to do that is just using bitwise operators. So we have unsigned int, I'm going to say concat is equal to, we're going to do octet 1, left shifted by 16, or is it, yeah, it's 16 because we need to shift it by 2 octets because we need it in the leftmost position or the most significant position, plus, or sorry, this should be just ORed or plus, it doesn't make a difference, but OR is less computationally expensive because we don't have to consider a carry. We have OR, I should put these in parentheses rather, just for order of operations. Then we have octet 2, left shifted by 8, and then ORed, bitwise ORed with octet 3, and that is not shifted at all. Alright, so we have our concatenation, so we have the bits concatenated. Now we need to take 6-bit groups at a time and output 4 characters. So we're going to access our output array now. This is going to be an unsigned as well. So we're going to index into our output array and we are just going to allocate and set our characters as needed. So we say encoded data, sorry, not encoded data. I'm looking at a reference that I stole from online. We say out at j++ because j is our cursor in the output. This is equal to, we're going to take 6 bits from this. So it's, to take 6 bits, we essentially want to get the most significant 6 bits. So we, for example, if we have 24 bits, let me just get a comments section here. It might be easier to draw this, but my tablet's kind of away at the moment. Screw it. We'll do this. Give me 2 seconds to open up OneNote. Where is OneNote? There we go. Perfect. Base64. All right. So we have taken, back on desktop. So we essentially have our 1101110. Let's say these are, that's another byte, and then we have our 3rd byte. So that's our 3 bytes, right? So we essentially need to group them into groups of 6, like so. So to do that, we just started by concatenating them. So we have 0110, 1110. Then we have the second one, 000, 1111, 5 ones, 11000, like that. So we have concatenated them using our shifters, right? So that and that. So this, let's say this is B1, B2, and B3. So this is B1 left shifted by 16 because we have 16 bits. B2 left shifted by 8. And then B3, like so. And then we now need to shift them again, or we need to now splice this into groups of 6 bits once we have them concatenated. So like so. And the way to do that is we just shift out and take a mask. So to start with, because we want this should be, how do I, There we go. Perfect. This should be our first character. This should be character out 1. I'll say out 1, then we have out 2, out 3, and out 4. So we want that as the ordering. So we're going to take these 6 bits as the first one. We're going to take, we'll say that's C, just concatenated. So we're going to take C and right shift it by, we need to right shift it by 3 groups of 6, so 18. So C right shifted by 18, and then we AND it with a 0x3f to only get 6 bits. This is equal to 0, 1, 1, 0, 1, 1. And that's this group. Then if we get the next one, C right shifted by 12 and 0x3f, this is equal to 1, 0, 0, 0, 0, 1. C right shifted by 6 and 0x3f is equal to the third bit, this one here, 1, 1, 1, 1, 0, 1. And then finally C no shift and 0x3f is equal to 1, 1, 1, 0, 0, 0, like so. And then these now have decimal values that will map to whatever indices in the table. I don't really care about them, but just this is the bitwise demonstration of it. So output at J ++ is equal to the table value. So we're going to index into the table, B64 table, and the index of it is going to be the concatenated value right shifted by 18 masked with 0x3f. And we have out J++ is equal to B64 table, concat right shifted by 12 and 0x3f. Then J++ is equal to B64 table at concat right shifted by 6 and 0x3f, like so. And then finally J++ is equal to B64 table concat right shifted by 0 and 0x3f, like so. I'm actually just going to create a new folder here, Base64, and just organize all this stuff in here. Oh, I closed that down, did not mean to. Move. Alright, so that should be it. So we've now shifted everything into there. And you will notice that we didn't really take account for padding. We are always outputting a multiple of 4. And this doesn't care if I was less than length, because if I is greater than length, we have a 0, which technically maps into an A, but that group of 6 zeros can also be a valid combination on its own. So we need to differentiate, hence the padding bits. So after we have output, we are going to essentially just take we're going to just put in some padding bits at the end. And to do so, I have that. I don't even know. How did I do this? So we're essentially doing what's called is unwrapping a loop here. In another implementation that I didn't unwrap a loop, and I had just one loop that output a Base64 character each time. But the way to map this to padding is, I'm forgetting now. Let's see. It depends on whatever the original length is. So you can use a table because depending on how the table, or what the input length, what its relative length is to 3, not relative, but depending on if it's divisible by 3, because if you think about it, if you have an input has 3 bytes or is a multiple of 3 bytes, it will always map to an even a multiple of 4 base64 digits, which we don't need padding for. So we then need to determine how much padding. So padding relative to, so we're going to do a switch on length modulo 3. And if we do case 0, padding is equal to 0. Right? If it's case 1, so if we have one extra character in here, so for example, if we had another 8 bytes over here, we would have to do, I believe it's 2. What's it? Yeah, it's 2. We would have to account for 2 padding bits or 2 padding bytes. So padding is equal to 2, and otherwise we only have to do 1. So if we have 2 extra bytes past a multiple of 3, we just have 1. Again, this isn't too crazy. Don't worry about the logic here too much if you don't care. It's just we're doing this for demonstration. And then we will say for integer I is equal to 0, I is less than padding I plus plus. We will say output at, is this going to be, let's create, okay, we already have out length. So output at out length minus 1 minus I is equal to the padding character, which is just an equal sign, like so. And then we return out length, because that's the length there. Okay, cool and cool. So this is 42 lines of code with the table. We can go ahead and try and compile this. So I'm going to go into CD B Base64, emsdk activates. All right, and then we have emcc Base64 c.c, and we want to compile it to Base64 c.wasm, because we're compiling this from our C file, and we just want to differentiate between two because we're now going to write raw WebAssembly. All right, so while we're waiting for this to build, why don't we go ahead and create our HTML file. So I'm just going to copy the existing one, keep this nice and simple. We'll have Base64. We're always looking for Base64 c.wasm. We have no name to consider now. And we just need to get a result. And we will input a string. So input type equals text, and I will say the ID is equal to text1. So what we'll say is now result is equal to exports dots, and we're just going to call our function here B64 encode, and we have to pass in a pointer. So I guess we have to frickin' we have to encode, we have to have the little string encoder, don't we? Oh, Jesus Christ. Did not account for that. So let's load string into memory. Variable string is equal to document.getElement by ID text1.value. And we're going to say variable array is equal to new uint8 array memory.buffer. So memory is from our exports. This is all just fetching this is just doing our WebAssembly streaming as per normal. Memory.buffer, and we want to say for let I is equal to 0, I is less than string dot length I plus plus. array at I is equal to string.charcode at I. So this was something that we screwed up last time, or that we screwed up with the structure encoding and decoding. In order to get the actual number, you have to say string.charcode at. So now we put it in memory, and we have it at, let's say, memory.buffer 256. So we'll start this at 256. The length is going to be string.length, and we will output this at 256 plus string.length plus 2. That's our output. Variable out address is equal to this number here. And then once we have actually called encode, we're going to now decode or get the encoded string from memory. So we're going to reset the array. So new uint8 array, memory.buffer, and it's going to be out address. And we want to say variable Base64 string is equal to empty. And we'll say while forward let I is equal to 0. I is less than result, because result is the length of the output. I++. Oops. And then we're going to just say Base64 string plus equals string dot from charcode, and the number we're going to pass in is the array at I, and then that's that. Like so. And then we can just print out our string. So console.log string encoded to Base64 string, like so. So now if I go ahead and do my HTTP server, I didn't open my browser. We'd love to see it. So I actually never even checked on whether or not did this even work? Error. I guess I need to do or actually did it even? Oh, it did it. No way. Okay. So it compiled it to a WASM file. Although I don't know if this actually has the exported function, but we can check, because we can use our, so I'm currently, let me just grab, here we go. Oh, I guess I never had a button to trigger. So inputs type equals button on click is equal to run module. Oops. Like so. So reload, and there's no text in there. It doesn't matter. ASDF. All right, this doesn't like it at all. But we can check out what we actually got. So we got a WASM file, and we can check out what we got using our tools. So wasm to what, base64 c.wasm, and we're going to output to base64 c.wat. And if we look in here, we see that there's a lot of imports. Probably because we screwed around. Well, I guess actually this is, or we never exported the function, that's why. But this is a short file because there was nothing to export. I mean, -16, I don't know what it's trying to do here. I think this is just basic stuff. Nothing crazy. So if we actually do go ahead and include emscripten.h and then have the emscripten keep alive tag to compile here. I guess I gotta compile this to JS. what will happen is now we're in our WASM file, and now I'm going to convert base64c.wat. We see that the file is much longer, but we do have our, where is it? B64 encode function, which has the function 1. So we need to find our function 1. All right, type 1 function parameter I32. So I'm going to look for this. Here we go. So it's just this. So this is function type 1. This is what we got. And wow, look at all of this. Oh, you can use offsets? I did not know that. That's cool. But yeah, look at all of this code here. There's a lot of loops, a lot of blocks, a lot of stuff. So much stuff. It doesn't return for a long time, and I can, you know, it's still going. It's still going. A couple hundred lines actually. We return at line 605 and we start at line 10. That's almost 600 lines of assembly code there, and we're gonna say screw them, and we're gonna write it on our own. But we didn't even test if this works. Let's reload. Okay, so this does work, I believe. Let me just make sure of that. B64 encode. YXNKZG 2 equal signs. Perfect. So this does work. Beautiful. We'd love to see it. Okay. So our goal is to now make this not happen in 600 lines. So we're going to create our new file, and we're going to call it base64.wat, because we're not doing this from C. All right. Our goal is to do this in under 200 lines. Way under 200 lines. So we're going to start with our module, right? That's what you got to have. We're going to have we're going to have one import statement because we want to import a console log for a number just in case we need it. Console log num, and we already have this imported from our HTML file here, which is great. And this is just going to be a function that takes in a parameter I32, like so. We also want to have memory to export because we need to access the memory as we did here. So we need to load the string into memory, and we also need to access the encoded string. So we're going to have memory. Remember, we call this, the way we define this, we have the memory tag, export, and we give it a name, exported memory, number of pages, maximum number of pages. We go export. We're going to export it with the name memory, and it's just going to be that memory tag there. Like so. So this, I'll zoom in here, give you some more space. So this little tag here maps here. And then we want to go ahead and define one of our things, one thing in memory first, to start at least. And that will be, where is it? That will be our table. We want to put this table in memory. I could have said this is a static character. I actually want to see what will happen if this is a static character B64 table. Oops. Let's see, do we have actually, I'm trying to figure out where this static memory is because we exported it as memory all the way at line 600 whatever, and we're still going. Okay, so here we go. So data 0, and it starts at I32 const 2024, so it's just a string right here, and this is our table. So we want to do the exact same thing, and I'm actually just going to copy this because I really don't want to put this in here. I don't want to type that out. So what you can do is that you can actually remove the last 0, because we don't really care about it, we as a programmer know that it's only 64 characters long. So we're going to say data 0. So this is the type, and it's going to start at I32 const, and we can just say we can keep it at 1024. Actually, let's put it at 0. We're going to do a funny little trick here. So this is our Base64 encoding table, right? Do I have all my parentheses closed? I have an extra one. That should solve it. Yes. Okay, perfect. So that's our encoding table. And now we're going to write our Base64 encode function. So the way to define it is just function, give it a name, Base64 encode. This is the local name. And then we export it as with a string name that can be called in JavaScript. Right there. So we export it as that. So we're going to have the same parameters as before. So we have a parameter string, but remember it's just a pointer, so it's an I32. We have a string length, also an I32. And then we have an output pointer, which is also an integer. And then we want to return an I32, which is the number of characters we wrote. So these are the 4 local variables that we're starting with. This result isn't really a local variable. It will be the last value on the stack. So essentially, I needed to say I32.const 0, and this be our result on the stack. This be our return value. So we're going to start with a couple of, I'm just going to declare our local variables right now, and you will see how they get used. So we have local length I32, which this is going to keep track of our output length, and you will see that our last line will just be local.get length. So this will be what we return. So I can actually just put that now, return length. And you can see that we are already done, and we have a 12-line function. Just kidding. I wish. It'd be pretty cool if there was like a hardware function that there probably is a hardware function that does Base64. It's super easy. But there's so many corner cases. Or, I mean, it only needs fruit for thought. Okay. We'll need a temporary value, local value. Also I32, but we will need to save this. Although we may be able to get around it, but I'm going to stick with what. Actually, local. No, we will need this as a local variable. Temporary value, local shift amount. This is just going to be a variable that we use to shift. And one of the strategies that we will also see as we go through this code is that when you write low-level code like assembly, being able to repurpose variables for 2 different uses is amazing, because if you only have to reference 1 variable instead of 2, you save memory, but you also save the reference. So you're saving memory in main memory, but you're also saving memory in cache, and you're also saving space, and it might also just make more intuitive sense with what you're trying to do. So we will see how this shift amount gets used as both a function. It has a function where we can use it as an amount that gets passed into some function call, but it also gets used as a counter. So that will be the amount to shift by, and then we will have a local min shift amount I32, and we will worry about this one later on. So that's what we're starting with 3 parameters and 4 local variables. This is compared to, let's see. How many local variables did the emscripten thing compile to? This has got to be, that's 612 characters selected. That's 204. That's 204 local variables. Yeah, we're not doing that. We're not playing around with that. So we're going to start just by initializing our output length, so i32.const 0 local.set length. And then we're going to go into our main loop. So we have main loop block. So the one thing I didn't touch on too much was how this block and loop works in WebAssembly. So if you have a block and you give it a label, say encode block, if we go through some code, so let's say we have a couple of statements, and you don't need a loop to put in a block, you can just put statements in a block here. So let's say the local.getString, local.getString length, and this is going to be our make condition that we will use. So if the string, the pointer here, is greater than our string length, then we want to break. So we say i32.ge_s, so greater than or equal to signed. And if this returns true, this will put true onto the stack, push it onto the stack. And if so, we want to break out of the block. And the way to break out of the block is, since this is a block, we can use this label, and when calling break, it will go to the end here. So this branch essentially just leaves the block. This is opposed to a loop, where we've seen with the WebAssembly here, using a branch statement in a loop, so pointing to this label in the loop will return to the top of the loop, so it will iterate. So the block, branching to a block, leaves the block, branching to a loop, iterates in the loop, but you must be within their block or the loop. So we actually forgot to do one initialization thing. We don't really care about the string length at this point. We really care only about the pointer, but because so if you remember, our condition is I is less than length. Now we really don't care about indices here. We care more about addresses. So to keep things more efficient, we are just going to compare addresses instead of indices, because it's going to result in the same thing regardless, as long as we increment it properly. The only thing where we do need to take care of lengths instead of addresses is the output length, because we need to return that, and it will also become important in padding. Right, so the other statement that we need before the loop is to set input cursor upper bound. So we're going to say local.getString, local.getString length, and we just want to put string length at the end of the string, so we're going to add these two and then set that as string length. So local.set string length. And we can actually put this in the encode block. Like that, this doesn't hurt, because this is directly related to the encode block. So we have these statements here, and we want to put these in the loop, because this is going to be our while condition. This is going to be our loop condition that we want to check at the beginning of each iteration. So we're going to have our loop. So loop, encode loop. And this loop here is going to, each iteration will process 3 octets and writes 4 Base64 characters. And this comment, you will notice, is the exact same as what we wrote in our C code. 3 octets output 4 Base64 characters. I will actually just make that the same so it's more obvious. So this condition check is going to be in the top of our loop. And you will note that this branch statement will still work because we are in the encode block. So if we iterate through the loop, if we start in the loop, and let's say the string length is 10, and we've iterated through 10 characters so far, we will see that the string pointer that we're going to use as our cursor is going to be greater than or equal to the string length, or the upper bound of the cursor, and hence we will have a branch statement which will just straight up leave the encode block, right? Because we have nothing left to do. All right, so we're going to start now by reading in our octets. So load 3 octets. And like I said, we're going to use a variable shift amount as both a functional description, it has a functional value, and a conditional value. So we're going to start in our block here. So block read octets block, and then a loop read octets loop. What you'll see often in WebAssembly is that loops and blocks will often be used in tandem because, again, if you want to branch to the block, you can essentially break out of the loop, but in order to reiterate or iterate back through the loop, you need to branch to the loop label. So before we enter the loop, we need to initialize a couple of variables. So we're going to start with resetting our value. So i32.const0 local.set value, just our temporary one there. And then we want to set our shift amount starting with the initial one. So we see that we started by shifting. So we're essentially going to load our value. So we're going to do this step octet 1 and then shift it into our value in one group of instructions. And we're not going to load each byte in separately and then combine them. We're going to load it and then immediately concatenate them. So we're going to store a shift amount as a variable. So i32.const16, because that's the first shifting here, this left shift by 16. And we're going to say this local.set shift amount. So in the loop, we're going to check this condition here again. So we want to do that. But instead of branching to the encode block, i.e. leaving the encode block, we want to branch to out of this read octets block, because we don't want to loop over any more characters if we've read all of them. But we do need to do some further processing because we have. So we will never enter this block here. We will never start reading if the cursor is already beyond what we have. But say, for example, we have 4 text characters, 4 bytes to read. We read 3 of them in the first encode loop. So this first one, we read 3, and then we have 1 left over. So the string cursor is not yet at the upper bound. So we enter the loop, right? We go through the read octets block. We enter the read octets block, and we read 1 character. And then when we loop back over, we don't have any more character bytes to read. So we want to essentially break out of this block, but we still have to do other processing beyond it. So we're going to say local.get string. So this is our input cursor. Then we're going to say i32.load8 unsigned. So the difference between, so there's a couple of things to digest here. i32 just means we're operating with integers. And we're going to load 8 bits. So we're going to load 1 byte unsigned. This just means that we will not sign extend the loaded value. So for example, let's just say that our byte was, instead of this 0 being here, we had a 1. So if we wanted to load these 8 bits in as a signed value, sign extending it would essentially just say, let's replicate this 1 all the way to 32 bits. And again, not too important right now. Point is, with unsigned, nothing happens. We just have zeros padding it, which is what we want. So then we say local.get shift amount, because it's the value amount to shift. So we load in bytes. Then we're going to shift to the left, i32.shift left. So we're going to shift the octet into position. Then we're going to say local.get value. And then we're going to combine this shifted value with the existing value. So we're going to say i32.or. So combine octet with existing concatenation. And then local.set value. Right? So notice how we're loading and shifting in one group of instructions instead of separating it into loading all 3 and then concatenating them. This makes sense for writing in C, but writing in assembly takes you need to think of it takes practice. It takes a lot of practice. It takes a lot of practice and considerations and optimizations, and it's a different mindset because you do need to consider what every single instruction does And there are tricks, there are hacks that you can do that your compiler will do for you. I mean, we saw that the compiler really didn't do much for us with this stuff here, but like if I wanted to say, so I need to find the value 16, I want to see, okay, well that's not what I was looking for. i32.store, nope, that's also not it. i32.const 16, it sets the 77th local variable. It's emscripten, there's a lot here, but I'm not gonna blame it because it's super powerful, because I didn't know how to write any of this. It's a learned art to write assembly, but these 7 instructions take care of reading in one value and then shifting it into the concatenation. That's all. So now we have done what we want to do in our read octet loop, right? And now we need to do the increment. So increment step. And there's going to be a couple things that we have to do to increment. We will start by decreasing the shift amount, because we don't want this shift amount to be 16 for all of them, because then they're just going to overwrite. So we need to say local.get shift amount i32.const 8 i32.subtract. Then we will set it shift amount. We also want to advance the input cursor. So local.get string i32.const 1 i32.add, so we're just incrementing it by 1 byte, local.set string. So again, another thing in assembly that we're considering here is we don't want to have duplicate variables, so we don't want to maintain a second counter here, because indices do not matter unless we use these offsets like we see here, but it's pointless to use it when we could just say, like for example, using a counter, we need this. But what we are doing instead is dereferencing data, then saying data plus plus. So we're taking the value at data, the 8 bits at data, and then we're advancing the cursor. And this is what we're doing with the plus plus. It looks better to use the array in C, but that's essentially what it gets compiled down to. We have an input cursor and we're advancing it. And then what we need to do is we want to have our loop condition, because again, we will exit out of this loop if there is no branch statement here. So we only want to loop, and we're going to use the shift amount as our counter here. So we're going to say loop if shift amount is not -8, because we still have valid data when we're not shifting. So it's the valid values of shift are 16, 8, and 0. So if we keep subtracting beyond 0, we get to -8. So if it's not -8, so we're going to say local.get shift amount i32.const -8 i32.not equals break if, or branch if, read octets loop. So we're going to only branch if shift amount is not equal to -8, and we can actually just say .gt just in case for greater than signed. So just to make sure that we are, just to be a little more, not equals is cheaper to do in hardware. Again, the way I am approaching this is as someone who has been working with assembly and who does work with low-level assembly and work with computers and their actual arithmetic logic units. So when I'm considering not equals versus greater than, yeah, it won't make a difference in the long run, or it will make a difference in the long run. It doesn't make a difference for a single line of code, but I'm just thinking the way not equals is implemented in an ALU, you essentially just need to compare. As soon as you find a single mismatch in a bit, you don't need to propagate any further. You don't need to propagate any further logic. But if you're considering greater than signed, you need to propagate through all 32 bits of those two values. Because I mean, you can start from the most significant bits and go down, but you still can't know for sure. The worst case is you go through all 32 bits, and that will happen more often than with a not equals. So that's all I'm doing here. I32.not equals. Again, doesn't make a difference. Computer's still going to run, but I'm just thinking about this as a computer engineer. Okay. So there's one extra thing that we have to consider here, and that is that where is this little condition here? I is less than length. And you do see that in the beginning of the loop, the read octets loop, and we completely branch out of it. And what you'll notice is that we're doing the same thing in C. So if we don't have a value at the data, it's going to be a 0. Because if we don't shift anything in, it's just going to be a 0. This 16, this 8, those are all hard-coded in. The difference is, however, I don't want to do this. I don't want to do a complete all 4 of these here. We could, theoretically, we definitely could. However, I don't really want to do this because this switch is kind of annoying, but the best way I found to do it is that we will set some flag in our reading loop that says, all right, do not reference the encoding table after some value. So the way we're going to do that is we have our min shift amount local variable here. And we will initialize min shift amount in each encode loop. So before reading the octets, so we have i32.const 18, and we will progressively decrement it. So local.set min shift amount. So it starts at 18, and you can see that is here. So if we don't find any characters, we don't want to shift at all. But if we find even one, we need to shift this whole concatenated block by 18 bits because that octet will already be in that position, or that sextet, I think it's called. But I'm not going to use that word because that's a funny word. But those 6 bits will already be in that position. So we need to have this set at 18, and then we will progressively decrement it. So we're going to say decrease minimum shift amount for next step. And all we're going to do there is just local.get min shift amount, i32.const 6, i32.sub, local.set min shift amount. All right. So this is all we need for our reading loop. So again, quick recap. Have our value, and we will read a single octet, a single byte. We're going to shift it into place. Now remember also, I guess I never explicitly said this, but WebAssembly works with the stack, right? So that's why I'm able to say load in the byte. So the byte is currently on the stack. So stack is equal to the byte. So now the stack, after we get the shift amount, is we have stack is equal to byte and shift amount. So then when we call shift, it essentially pops the 2 values on the top of the stack, the byte, then the shift amount, and it will left shift the byte by the shift amount. Sorry, I misspoke. It pops the shift amount, then the byte, and it will use those as the two arguments into i32.shift left. So then this value is now on the stack. So stack is equal to byte left shifted by shift amount. Then we get our value. So stack is equal to byte left shifted by, I'll say byte prime. Oops, byte prime and the value. And then now we are just ORing them together. So byte ORed with the existing value, and then we set that in our local value. So that's how these 7 instructions work together to change the value. And it should be noted that we have, let's see, 1, 2, 3, 4, 5 of these instructions are memory instructions. And i.e. getting, if this was an ARM or this was some other sort of assembly where we were working directly with the CPU, these would be 5 memory instructions because, again, these are variables and 2 register-to-register instructions. But that's beyond the scope of this. So that's the reading loop. Now let's move to our write loop. So we will write 4 base64 characters. So we will start with our block, output block. Oops. And we'll have our loop, output, output loop. And just like here, just like with the read, we're going to have our shift amount set to some value, and that initial value will be 18 as we set here, as we saw with the C code. So i32.const 18 local.set shift amount. Output loop. So this is going to be another set of instructions that will just do a bunch of things for us. So we're going to start by getting our value. So local.get value. So we'll write the instructions and then we'll do a stack analysis. So we have the value on the stack and we want to shift it. So local.get shift amount. Then we're going to say i32.shift right unsigned, because we don't really care about, we don't want to essentially shift in ones. We want to shift in zeros. So we shift to position, and then we're going to have a bit mask. So i32.const 63, and that bit mask is just this and 0x3f. i32.const 63. Then we have i32.and to apply the bit mask. To get this those 6 bits, and then we are going to, so we have our value that is less than 60 or 63 or less than 64. We know that, but now we need to essentially do this encoding step. So we have the value, we have shifted it, and we have gotten the value, but now we just need to do this step. And if you remember, we have our table up top and it starts at address 0. So to index into this table is essentially to index into, do a load starting at address 0. And lucky for us, all we have to then do is just say i32.load8 unsigned, because this masked address is just the raw address into the table. Now I believe if we have offset is equal to 1024, for example, then we can then set this to whatever address we want. But I'm going to leave it as 0 because I know that that's what works. And then we have this in our stack. So the encoded characters in stack. Now, if we were to say i32.store 8, or just store 8, I want. Oh wow, I almost screwed that up. So we want to say i32.store8 to actually write the output character. But the way this instruction works is it takes the address first and then the character. Cool thing is we can just load in the address beforehand, because these 6 instructions work completely independently of anything else, regardless of what's already on the stack. Because get value and get shift amount put 2 new values on the stack. So let's look at this here. Stack is equal to value. Then stack is equal to value and the shift amount. Then we have the stack is equal to value prime. Stack is equal to value prime and 63. Then we applied the mask. So the stack is equal to the value and 0x3f. So I'll say value prime and 0x3f rather. And then we loaded the value, so stack is equal to character. And now we need to store it. But again, we need something before this character as the address, and we can just do it by loading in the address beforehand. So local.get output, which is our output cursor. And again, this stack is completely independent of what comes beforehand. So now the stack is out and character, and then we just store character. So we have 8 instructions to get the value, shift it, mask it, apply a bit. So we shift it, mask it, get the encoded value from the table, and then store it. Beautiful. 8 instructions to do that. And then we're going to do our increment step. So we have local.get shift amount. And it's going to be i32.const6, i32.sub. This is the same as before, just using 6 as our increment. And then local.set shift amount. Then we're going to increment the length. Local.get length. i32.const1. i32.add. Local.set length. Oops. We will do the same thing with the output cursor. So this is out. And then our condition will now be down here. So loop if shift amount is above the minimum. So again, the minimum is some local variable that we set in the previous loop, this one here. So we're just going to compare the shift amount to the minimum. So local.get shift amount, local.get min shift amount. Then we say i32 greater than or equal to signed, break if to the output loop. So if the shift amount is above the minimum, then we branch back to the beginning. Otherwise, we can just fall through these, and we don't need an explicit break instruction from the output block. And also, we have an implicit branch. So I'm just going to put this in comments because it's implicit. But branch output block. And then also branch. This is the encode block. So these are all implicit. But because there is no... Or actually, sorry, this has to happen here. Branch encode loop. Sorry, wait, this must be... I'm thinking, hold on, I may have screwed up my stack here. Or my... Sorry, where is the encode loop? This is the encode loop. Okay, no, it's good. So we are always going to branch back to the beginning of the encode loop, this thing here. And then we will check the condition of the cursor up top, right? I suppose, you know what, we could actually, since we check it at the beginning. Oh wait, no, sorry, we don't even check it at the beginning. That's wrong. This is not the same. All right, so this is good. So we branch back to the beginning and then break if needed. So the last thing we have to check, last thing we have to consider before returning is our padding. And then also our terminator character. I'll take care of the terminator character first because it's easier. So local.get out cursor. This cursor is staying with us the entire way through. i32.const 0, i32.store 8, store 1 byte. For padding, we're going to have a block because again we want to be able to break out of it. And then we will have a loop, pad loop. So the couple of strategies that will reveal themselves is if you have a while or a for loop where the condition needs to be checked at the beginning of the loop, you need to have a block plus a loop. Because in that case, you can then check the condition at the beginning. Let's see, like right here, for example. And if it does not work, if the condition does not pass, you can leave. But you can check, the point is you can check this condition using the incremented or initial values. Now, if you have a do while loop, something like over here with the output loop, I suppose we don't even need this output block. Although I will check that because this condition is checked at the end. So it should not even be needed, but I'm going to leave it for now because I'm not entirely certain. But because we never need to explicitly branch out of this loop, this block tag should not be needed. But I'll check that afterwards. All right, so for our padding loop, the condition is break if no more characters to pad, i.e. if the current length is not divisible by 4. So that's just remember our output has to have a multiple of 4 characters. So we're going to check that with local.getLength, i32.const 3 as a bit mask, i32.and, and if this is positive, so if this is a non-zero value, then we want to keep going. However, there is no way to say branch if not. So we have to explicitly do a comparison with 0. So i32.const 0, i32.equal, and if they are equal, then we branch out of pad block. Break if no more characters to pad. So break if not divisible, or if divisible by 4. Like so. All right. We will then it's a simple loop. We're going to store our padding character. So local.gets output. This is our cursor. i32.const 61. Padding character. This is just the equal sign. And then i32.store 8. Then we want an increment step. Oops. So the length local.get length, i32.const 1, i32.add, local.set length, and then the same thing for the cursor. So local.get outputs, i32.const 1, i32.add, and then local.set output, like so. And then we will always branch back to the beginning of the loop, where we will be looping and checking the condition afterwards. So that is it for our function. Let's compile using WAT to WASM. WAT to WASM base64.wat. No errors. Would you look at that? I mean, I have been looking at my reference, but usually we get some errors. Let's actually, just for thought experiment, let's say WASM to WAT base64.wasm, and we want to output this to base64 wat.wasm, wat.wat, just so I can see what the assembler generated versus what the C compiler generated. So we have base64 c.wat, but then we also have base64 wat.wat. Oops. So if we put these side by side, we can first of all see that the lengths, we have 119. Oh, that is a big improvement from what I wrote. It's just a lot. There is no white space here. That's the difference. So base64 c.wat has 600 lines. Base64 wat.wat has 200 lines. They both have loops. So you tell me which one is better. This one uses 4 local variables. The compiled one uses 203. It's freaking ridiculous. 204. But you can directly see the way the assembler works, and it's much easier to map your code using the assembler. We have our 4 local variables right here. That's declared right here. It doesn't use the assembler doesn't use names, but we have our constant value local.set3. So now we know that the length is the index 3 local variable. We have a block. These 4 instructions are still there, so you can map directly to and from. Let's go to our HTML file, and let's now, instead of streaming from base64 c.wasm, let's do base64.wasm. So we'll reload ASDF. Aha, it works. Beautiful. So that's 4 characters. Let's do G, H, and you'll see that there are no padding characters here. Because one, the output is 8 characters, so a multiple of 4, but then you can also see that the input is 6 characters, a multiple of 3. And 3 characters maps perfectly to 4, so we have 2 groups. Whatever. Let's see if this is correct, and if it is, I'm done for the night. B64 encode. Okay, it looks right. All right. Yeah, that's it from me. I hope you guys learned quite a bit today. This was a fun one. We did a lot with assembly, and God, there's so much more to do. But it's a lot of fun. It's a learned. Please rewatch this video as many times as you need. Writing assembly is difficult as hell, and it's heart-wrenching, and it was heart-wrenching for me to do this. But just keep going, keep doing it, and you will get the hang of it after some while. I've been writing assembly for over a year now. I learned my first assembly code in, I want to say, about a year ago. Like a first explicit course on assembly about a year ago. A bit over. But it's been writing this code itself was difficult, because that mapping is not always one-to-one. You can't always explicitly unroll these loops like so. I mean, you could, but you would pull your hair out writing 600 lines of code to explicitly map all of this. But we're here. We're done. Hope you guys enjoyed, and I will see you guys next time. Have a good one.